All right, today we're going to start by talking about separation of variables. We're going to conclude where we left off last time. And so we started last time by going through a separation of variable problems with an x dimension and a time dimension, one spatial dimension, one time dimension. And the goal of this is to try to separate out the solution in terms of a function that's just a function of x and a function that's just a function of t, and then solve those separately, those ODEs separately. All right, so last time we got as far as going through identifying the homogeneous direction solution, which was we called theta x. And actually I didn't write that here, but it's theta x. Theta x was equal to C2 times cosine of lambda x. And then we had enforced the boundary conditions for this problem in order to get to, in the homogeneous direction, to get to a eigencondition. And the eigencondition is tangent of lambda L is equal to h bar over lambda k. All right, so we have this periodic solution which gives us a bunch of different lambdas, and that's our form of the solution in the homogeneous direction. Okay, so we are this far. Now our task is to solve the non-homogeneous problem. And remember, the non-homogeneous problem here was the function of time. And why is it non-homogeneous in time? Well, because we have an initial condition in which there are things that appear that are not multiplying time or its derivatives. Okay, so we have this ODE in time. Again, we got to this point by deciding that the lambdas have to be positive in both of the cases, both homogeneous and non-homogeneous, because they have to equal the same constant, right? So the non-homogeneous is positive because the homogeneous was positive, and they both equal the same constant, lambda squared. Okay, so we have our lambdas now. We go back and solve the non-homogeneous ODE. So this was the non-homogeneous ODE that we needed to solve. And the solution for this is actually just exponentials because we have the derivative plus the function again times some constant has to equal to 0. So that's satisfied if the form of the general solution is exponentials, as we see here. Right? And if you don't remember that, you could probably plug it into Maple if you wanted to do that, or go look it up in a table. But this is the solution for the non-homogeneous direction. Okay, so we take this now. We have an individual solution for each eigenvalue, each of the ith eigenvalues. And so that becomes our ith time solution corresponds to an ith constant and an ith eigenvalue. All right, so that's step 4. And then step 5 is we're going to determine the temperature solution for each eigenvalue. And that involves bringing the x direction solution and the t direction solution back together. So for a given eigenvalue I, we bring together the solution as the product. That was our original separation of variables assumption. Okay. So now we have our ith solution, theta I, is the product of those two things. We have our x solution, C2i cosine lambda I x, times C3i exponential of minus lambda squared alpha t. Right, those two things multiply. Well, the product of two unknown coefficients or constants is another single unknown constant. So we'll just call that Ci. Okay, so we've now got down to one set of Ci's that we need to solve for. Fortunately, we have our initial condition that we can enforce as our last boundary condition. Okay, before we do that, let's assemble all the solutions back together by summing them up, and we're left with the summation of all i's is equal to this solution. Okay, so then step 7 here now is to enforce the non-homogeneous boundary condition, or single boundary condition here in time, and we're going to do that using our initial condition. All right, we have our expression, we have unknown constants, we need to enforce the boundary condition. So how do we do this? What is our boundary condition, first of all, in the non-homogeneous direction? Right? It's our initial condition. The non-homogeneous direction is time. So we have an initial condition in that direction, that time direction. We need to enforce that. So our initial condition is given here. Right? This is our initial temperature profile, which is the temperature profile due to the generation, right? It's at steady state generating, and then we sort of turn off the generation. So this temperature profile here is our initial temperature profile. Okay. So we have to plug that in. We do that. Now we have this function here. This is our evaluation at, let's see, look back up a little bit here, right? So we're evaluating this at time equals 0. So this term goes to 1. Exponential of 0 is 1. So we end up with down here, this evaluated at time equals 0 has equaled to our initial condition, right? Now, what's the problem with this? Again, we have a function of x in the thing that is supposed to give us the unknown constants. So we have to figure out how to get rid of that function of x, and we do that using orthogonality. Okay, so we multiply it through by our eigenfunction on both sides, right? Cosine of lambda times x is our eigenfunction. So we're going to multiply that through, and we end up with, on the left-hand side, cosine squared, and we take the integral of that from 0 to L. And then on the right-hand side, we have this whole thing, right, being multiplied by our cosine function. And we have to integrate each of them, right? So we end up with an integral here, and we end up with an integral here, okay? So you can then go through and do that in Maple if you're so inclined. So that would look like this. So we would have our 3 integrals that we would bring over, do those in Maple, copy the results, take it back to ease, and we can look at the solution in ease. Okay, so this is this problem implemented in ease. Again, it's the same thing you've seen before. We've got our eigenvalue solution here, or the guesses here, and then the eigenvalue solution here, right? And then now we're duplicating, but we have 3 integrals for this particular problem that we're implementing. So for each of the lambda i's, we have this integral solution, and then this is the equation that we use to get the constants from that. That's our boundary condition. And then here's our full solution implemented down here. Okay. So then we calculate back the transform. So we were doing this for theta, right? So now we have t plus t infinity is the actual solution. And it's in C. And so you could solve this, and we would get a single value of temperature, because we're evaluating this t here. We're evaluating this at a specific position and at a specific time. Okay. We would go through and maybe plot it as a function of position, and it would look like this. So this is at sort of steady state condition. But we could also plot it at different times, and this is what the solution looks like. Okay. We went through that fast, sort of, but do you sort of all follow? Have any questions on that? Okay. Okay, good. So that's separation of variables. Okay. Limitations of separation of variables is the x direction has to be homogeneous, right? Otherwise, it's not going to work because t is almost never homogeneous. Okay. So you can really, you can solve problems where that's true, but what happens when you don't have that condition, when you can't satisfy the requirements for separation of variables?